Okay, our next speaker is Kristina Ilenko from Ekaterinburg.
Thanks for the introduction. Good afternoon, dear participants of the conference. First, I would like to thank the organizers of the conference for the opportunity to make a talk, and namely, I would like to tell you about the results of research which were received with my supervisor, Natalia Vladimirovna Maslova. The topic of my speech is coincidence of Gruenberg-Kegel graphs of non-isomorphic finite groups whose Gruenberg-Kegel graphs are disconnected. So let's start. In our research, we used standard definitions and notation. So we use the term group while meaning finite group. We use the term graph while meaning I-directed graph without loops and multiply edges. The subgroup of a group G generated by all minimal non-trivial normal subgroups of G is called the circle of G and is denoted as indicated on the slide. A Frobenius group is a group G containing a proper non-trivial subgroup H such that for all G in the difference of set H from the set G, the following equality holds. Any Frobenius group is a semi-direct product of F and H, where F is a non-trivial normal subgroup of in G. The subgroup F is called the Frobenius kernel of G, and H is called a Frobenius complement of G. A two-Frobenius group is a group G which can be represented as a product of A, B, and C, where A and AB are normal subgroups of G, AB and BC are Frobenius group with Frobenius kernels A, B, and Frobenius complements B and C, respectively. Note that any two Frobenius group is solvable. Now I would like to give an example of a Frobenius group. So let F is a finite field, and order of multiplicative group is equal to Q minus 1. Let multiplicative group act on an additive group by the rule on the slide. Now let's try to form a semi-direct product with respect to this action. After that, we can call G as a Frobenius group with the Frobenius kernel, which equals to an additive group, and a Frobenius complement, which equals to a multiplicative group. Now I would like to recall a few more definitions. Let G be a finite group. Group G is called simple if G has no proper non-trivial normal subgroups. The spectrum omega G is the set of all element orders of G. The prime spectrum pi G is the set of all prime divisors of order of G. We use the term Gruenberg-Kegel graph of the prime graph of G while meaning the graph gamma G, whose vertex set is equal to the prime spectrum of G, and two distinct vertices P and Q are adjacent if and only if in G we can find an element with order which is equal to product between P and Q. Note that the research of properties of a finite group by properties of a Gruenberg-Kegel graph has been actively developing since the beginning of the 21st century. Namely, cases of coincidence of Gruenberg-Kegel graphs are actively studied. This research allows us to draw an analogy between the complex internal structure of groups and the less complex structure of its Gruenberg-Kegel graphs, which in the future may contribute to expanding the range of applicability of the finite group theory. Let's recall a Gruenberg-Kegel theorem. The Gruenberg-Kegel theorem describes all groups with disconnected Gruenberg-Kegel graph, so it is a useful and interesting result. If G is a group with disconnected Gruenberg-Kegel graph, then one of the following statements, which you can see on the slide, holds. From the first, it follows that G is a Frobenius group. From the second, it follows that G is a 2 Frobenius group. And from the last, it follows that G is an extension of a nilpotent group by a group A, where the follow inclusion holds. S is a simple non-abelian group with disconnected Gruenberg-Kegel graph. We were interested in the problem of coincidence of Gruenberg-Kegel graphs of groups taken from different statements of the Gruenberg-Kegel theorem. In other words, let G be a finite almost simple group and H be a Frobenius group or a 2 Frobenius group of the Gruenberg-Kegel theorem. And then the main problem of our research is a description cases of coincidence of graphs gamma G and gamma H. Now I would like to cite the results of previous researches on the Gruenberg-Kegel graphs. In 2012, Mariana Zinovьeva and Viktor Mazurov considered the cases of coincidence of graphs when G is finite simple group and H is a Frobenius or a two-Frobenius group. In 2016, Mariana Zinovьeva and Anatoly Kondratyev determined the list of all finite almost simple groups such that all connected components of the Gruenberg-Kegel graphs are cliques. In 2018, Ilya Gorshkov and Natalia Maslova showed conditions when Gruenberg-Kegel graphs of finite almost simple group and some finite solvable group are coincide. Thanks to the result obtained in 2016 and 2018, we know on the cases of coincidence of gamma G and gamma H when G is a finite almost simple group and H is a solvable Frobenius group or a two-Frobenius group. The case of coincidence of gamma G and gamma H when G is a finite almost simple group and H is a non-solvable Frobenius group is the last case which earlier is not considered. And in our work, we explore this case. In other words, our research is relevant because it was necessary to complete the description of cases of coincidence of Gruenberg-Kegel graphs of finite almost simple groups and of Frobenius or two Frobenius groups. On this slide, you can see the result of our research. So let G be a finite almost simple group, H is a non-solvable Frobenius group. Assume that gamma G and gamma H are equal. Then one of the following conditionals holds. From the first, it follows that so-called G is a sporadic group and G isomorphic to the automorphic group by M12 group. From the second, it follows that so-called G is an alternated group and G isomorphic to S7 group. And from the third, it follows that so-called G is an exceptional group of Lie type and G is isomorphic to the automorphic group of Tis group. For classical groups, we obtained that either G is isomorphic to the one of the groups listed in items from 1 to 4, or G is a small group with so-called PSL3Q or PSU3Q, for which the statements on the slide are true. Note that this notation is a standard notation taken from the Atlas of finite groups. And our research is still in progress, but will be completed soon. In 2016, Ali Mahmoudifar considered the problem of constructing a non-solvable Frobenius group whose Gruenberg-Kegel graph coincides with the Gruenberg-Kegel graph of PGL 249. That is a separately given almost simple group. His research confirms that the problem of coincidence is interesting. But we can understand when a non-solvable Frobenius group exists and when it does not, for all groups with so-called PSL2Q. And if such a non-solvable Frobenius group exists, then applying the research by Mariana Zinovьeva and Viktor Mazurov, we can immediately build such a group and its Gruenberg-Kegel graph. Let me now consider some tools which were useful in our work. In our research, it was important for us to understand what Gruenberg-Kegel graph of a non-solvable Frobenius group looks like. The first is a proposition which is obtained in research by Mariana Zinovьeva and Viktor Mazurov. Let H be a non-solvable Frobenius group, then gamma H has two connected components. The first component contains 2, 3, and 5. Moreover, if P and Q belong to the first component of gamma H, then P and Q are non-adjacent in gamma H if and only if the set which consists of P and Q and the set which consists of 3 and 5 are equal. And the second component is a clique. For each labeled graph gamma with these properties, there exists a non-solvable Frobenius group H such that gamma H and gamma are equal. So to solve our problem, we need a list of almost simple groups whose Gruenberg-Kegel graph has these properties. The next tool is a Gruenberg-Kegel theorem, which received in 1981. Besides, separately in 1981 by Williams and in 1988 by Anatoly Kondratyev, were described connected components of Gruenberg-Kegel graphs of simple non-abelian groups. And in 2005 and in 2011, Andrei Vasilyev and Evgeny Dovin received adjacency criteria in Gruenberg-Kegel graphs of simple groups. And the last one is D Theorem, which is an important number theoretic tool when working with a Gruenberg-Kegel graph. Let's start with the definition. So, if R is an odd prime and Q is a natural number, which is more than 1 and coprime to R, then there exists a number which is denoted as EQR, and which is equal to minimum of all E, such that Q to power E is equal to 1 modulo R, and E is a natural number. So let Q be a natural number, which is more than 1. Then for all natural M, there exists a prime R, which denoted as this, such that EQR and M are equal, except cases on the slide. Also, I would like to tell you one fact about prime R. The prime R, which satisfies the condition on the slide, is called a primitive prime divisor of Q to power M minus 1. That is all. Thank you for your attention.
Kristina, thank you very much for a very nice talk. Are there any questions to Kristina? Well, then I have a very simple question. In your talk, there is a theorem with some results. Actually, there are 5 cases, and you said that these results are in a progress. So my question is, which of these cases is more complicated for you?
I think it is the case of PSL2Q and PSU3Q and PSU2Q.
Mhm. I see. Okay, I see. But
Can I make a small
yeah, sure, of course, yeah.
as a co-author. Here, in the case PSL2Q, there is a very hardcore number theory.
I see.
For cases PSL3Q and PSU3Q, there are other complicated moments connected with group theory, but PSL2Q is very complicated in sense of number theory.
I see. Well, does this mean that the first three cases are done?
Yes.
I see.
Unknown cases are only for groups with linear and unitary circle of dimension 3 and for very small, not many possibilities for the field characteristic. So I think it will be ruled out very soon.